Shall we? I think it's time. So, welcome back. Today we will continue with discussing topological dynamics of cellular automata, and we will hopefully finish the chapter. So, let's start with some recap. So let A be a cellular automaton in dimensions T with state space S and global rule F. Be a CA. So last time in a series of propositions we proved the following. So we proved that a CA is surjective if and only if A is pre-injective This was the Garden of Eden theorem, and since it holds that injectivity is a stronger property than pre-injectivity, then as a special case we get that injectivity implies surjectivity, and therefore injectivity is equivalent to bijectivity. And as we discussed at the beginning of the class, this is equivalent to A being reversible. And one more criterion that we discussed is that surjectivity is equivalent to A being balanced. And maybe a good remark, so that it's not confusing, is that essentially, let's say that let F be the local rule. So there are two notions. Either A is balanced or F is balanced. So when we talk about the rule table being balanced, we literally mean this one function having the same number of outputs for each state. But the whole CA being balanced is a stronger property, and this is defined as all the possible unravelings of the local rule being balanced. And how does the unraveling work? It just takes an arbitrarily big pattern and it applies the local rule everywhere it can, and it outputs another finite pattern. So in some sense, for every k, this is a function from S to the k plus 2r to the power of d with radius r. Yeah. And the output are patterns where we reduce the size of this cube by r from each side, so it's just k to the d. So just so that you don't confuse these two, they are not the same. And I promised I will show you an example of a CA that is surjective but is not injective, so that we know that injectivity is a strictly stronger property. So let's do that. So rule 90, which is just defined as f of x, y, z is x plus z modulo 2. is surjective but not injective. So let us look at why. This will be a good intermezzo for a definition, which we can only discuss in 1D. So let A be a 1D CA with radius R and local rule F. So we say that A is left permutive if you look at the local rule, you leave the first input to be whatever, and you fill the rest in any way that you like. Which is just a function from S to S. So we want this to be a bijection for any possible values. So it kind of makes sense to call it left permutive. It's permutive in its leftmost component. Is a bijection for all possible ways to fill the rest. And now you can guess what will be right permutivity. If the same holds for the rightmost component. Bless you. Is a bijection yeah. Again, for all possible ways we can complete this. So now we can observe that rule 90 is both left and right permutive. That's quite easy to check. So and all 1D CAs that are both left and right permutive are quite special. We will now show that it is surjective. And in the case of rule 90, essentially, we will show that every binary configuration has exactly 4 preimages under the global rule of the CA. So I'll just draw the reason. So suppose we have some binary configuration. And we are interested in constructing a preimage. So you can pick your favorite starting position, for instance 0 and 1. And let's pick B0 and B1 arbitrary. And now, due to the left and right permutivity, there is exactly one way we can start extending this partial preimage to be an actual preimage under rule 90. So there is exactly one way this pattern can be extended to a full preimage of C. So if we want to determine what's here, we essentially just use the left permutivity. Essentially, we have the output, and we have these two cells. So we know that there is exactly one solution to this. So we just fill this value to be exactly that unique value. And as you can see, using left permutivity iteratively will allow you to extend this partial preimage to the left, and using right permutivity will allow you to extend it to the right. So hopefully that's clear. So yeah, this shows that rule 90 is surjective but not injective. Are there any questions? Nice. So with this we can start a mini subchapter about equicontinuity and surjectivity. So what we have covered now is really just some of the most basic properties of the global map of a CA, that is the continuity, surjectivity, and injectivity. There should be sensitivity. But there is a pretty rich theory of cellular automata as these maps of topological spaces. In particular, there is a variety of notions which characterize how sensitive a cellular automaton is when you perturb its initial configurations slightly. And we will not cover this in depth because we don't have enough time, but I'll just talk about these two notions and how they can be used to form a classification of cellular automata from a topological perspective in dimension 1. So I suppose we can already, so let's fix some d-dimensional cellular automaton for now. So the first definition so we will call a configuration an equicontinuity point of A if somehow it is if f is continuous in C, but not only f, but all the infinite family of iterations of f. So C is an equicontinuity point of A if for every epsilon larger than 0, there exists a delta larger than 0, such that for all iterations of f and for all configurations C prime, we have that if the distance between C and C prime is less than delta, then the distance of an arbitrary iteration under F of C and C prime is less than epsilon. So essentially, yeah, this means that the whole family, so f squared, f to the power of 3 is continuous at C, let's say with the same delta for a fixed epsilon. So by E of A, we denote the set of all such equicontinuous points of the CA. Equicontinuity points of A. And lastly, we say the CA is equicontinuous if every point, if every configuration is an equicontinuity point. So A is equicontinuous if the set of its equicontinuity points is the whole configuration space. So a trivial example of this is just the identity CA, where the iterations are all the same. So the identity CA with FC equals C for all C is equicontinuous. And in some sense, this class does not offer a much more interesting behavior. So this is a claim that I will not prove. It's not hard to prove, but we don't have the time, but it's more just for illustration. So essentially, A is equicontinuous if and only if there exists some pre-period P and there exists some cycle length of positive value C such that F to the power of P is the same as F to the power of P plus C. So let's maybe not be so restrictive. So natural way to, let's say, loosen up this property of equicontinuity is to be almost equicontinuous. So A is almost equicontinuous if the set of its equicontinuity points is residual. So who here would like me to elaborate on what residual means? So depending on in which field in mathematics you are, there are different ways to define what a very large set means. If you have a measure, it could be like you can define the size based on the measure, but in topology, let's say a residual set is the topological sense of a set that is being large. So Yeah, I don't know. I said E is residual if it contains a countable intersection of dense open sets. So then, for a reasonable topological space, this means that this set is large. For instance, we have a claim that in a complete metric space, each residual set is dense. So, and we are in a complete metric space because we are, so such as, because we are in a complete, in a compact metric space. And a property that holds on a residual set is, let's say, typical or generic in the topological sense, or like with the tools we have, which is a topological space, this is how we can define a property to be a typical property of the system. So why this is natural? Like, for instance, there is the nice property that if you have, so if P is a typical property and Q is a typical property, then their intersection, or let's say then their conjunction in the logical sense is also a typical property, because you can just take the intersections of the two countable intersections. So it's kind of robust to countable intersections. So one example of a residual set in the space of cellular automata, so end of small remark. So E, which is a subset of binary configurations defined as the set of all configurations where C contains infinitely many ones, that is a residual set. Is a residual set. So proof. Essentially, we just have to decompose this into imposing countably many conditions on E and taking an intersection of these conditions. So we can define En to be containing exactly such configurations where there is a 1 at some position I for some I less than minus n, and there is also a 1 at some position j for some j strictly larger than n. So now it should not be hard to see that E is indeed an intersection of such sets. So clearly, if a configuration contains infinitely many ones, then it contains a one arbitrarily far away, so it belongs to all of these. And on the other hand, if a configuration belongs to all of these, then it belongs to E1, so it contains two ones. Then you can look at the indices that are far further than these two witnesses, and then it's going to belong to that set, and you can iterate the argument. And on the other hand, it should also not be hard to see that for each n, this is an open and dense set. So yeah, it is open because if a configuration belongs there, it has these two witnesses of ones, so the ball that has a radius larger than the positions of these two ones will all be contained in such an En, and it's also not hard to see that En intersects with every ball because yeah, you can just specify the configurations at this, let's say, box of the ball, and then you can always find two ones that are further away, and so it's going to intersect with En. So this means that indeed, let's say sets of this type are residual. Are there any questions? Good. So now we can turn our attention to, in some sense, an opposite property, which is the sensitivity. Okay, good. So A is sensitive if, let me have enough space for this, there exists an epsilon such that for all configurations and for all delta, okay, let's say C, okay, for all C prime, it holds that, okay, there exists, yeah, that's the important thing. You can always cleverly choose some C prime, which is arbitrarily close to C, so the distance between C and C prime is less than delta. Okay, and there exists an N. I think it does not matter. Such that the distance between these two iterations, okay, let's do C, F and C prime, is larger than epsilon. So what does this say? This says that there exists one universal resolution window around the origin, such that no matter what configuration you start with, C, you can choose one clever configuration C prime that's gonna agree with C for as long as it needs. But as you start iterating the global rule from both, eventually their difference will manifest in this finite observation window. So, yes?
Here between the delta and the rest, is it supposed to be an equality
Implication, of course, that would be, what would that even mean? Yeah. So now we have all the definitions we need, and so let's start establishing some relationships between these notions. So the first observation we can make is that if A is sensitive, so maybe an example, just a quick example. So you're happy there are examples. For instance, the binary CA and the left shift is sensitive. Why? You can just even pick this epsilon to correspond to the finite resolution window being just the single cell at the origin. And no matter what delta you choose, you can always find two configurations that are the same on this window but will eventually differ somewhere to the right. And this difference, as the shift continues, will eventually manifest at 0. What should be pretty clear now is that if A is sensitive, then the set of its equicontinuity points is empty. That is, if A is sensitive, then in particular we can exchange these two quantifiers and have that for every C there exists an epsilon such that for all delta, and this is exactly for all C, negation of the statement that C is an equicontinuity point. So in particular, A is sensitive implies A cannot be almost equicontinuous. I hope we all agree on this. Is it clear? So now we have been talking about the general dimension D, but now it becomes extremely important that we only restrict ourselves to dimension 1. So let's say a subtopic is topological classification of 1D CAs. So now the important proposition that only holds in dimension 1 is that let A be a 1D CA. So then if A is not sensitive, then it is almost equicontinuous. So what this means is that in 1D, every CA is either sensitive, or let's say either almost equicontinuous, So, in particular, this nice dichotomy can be seen as one possible formalism which splits between the Wolfram classes 1 and 2, where all the behavior converges quickly to some small attractors and the CA is not sensitive to perturbations, and to classes 3 and 4, which could be represented by the sensitive CAs, where for every configuration you can find a difference that will eventually manifest. And that's very nice, but yeah, we should not take it exactly, because there will always be some rules which intuitively, in the Wolfram sense, would be considered class 1 or 2. For instance, the shift, it does not really create any crazy space-time diagrams, but in this topological sense, it is quite chaotic. So we did not really get to talk about some notions of chaos, but it is clear that the shift is sensitive. So yeah. So let me just summarize this. So we can view this dichotomy as one way to formalize the distinction between Wolfram classes 1 and 2 and classes 3 and 4. So let's gain some intuition behind why that proposition holds in 1D, so this does not feel just as a black box. And I will illustrate it through an example. So let's consider an elementary cellular automaton be the majority So what does this mean? It just means the local rule always outputs the majority of its input bits. Then, so let A be this. Then A has a so-called two blocking word zero, zero. So I will only talk about this intuitively. But it's very easy to see that as soon as a configuration contains the two cells 0, 0 right next to each other, these will never be outvoted. It does not matter what opinion is present here or here. Essentially, these two cells have solidified in their opinion to be 0 forever. So it does not matter what is the rest of this configuration. In the space-time diagram, this will always be two zeros. And we can use this fact to show that A is almost equicontinuous. In fact, it's a very simple argument. So let E be the set of configurations such that C contains the pattern 0, 0 infinitely often. So then there are essentially two claims. So E is residual. This should be clear because it's the exact same argument as the example I just showed you. You will again be able to decompose E into an intersection of countably many conditions. And second, every point in E is an equicontinuity point. Of A. So suppose you, so why is that? So let's say pick some n, which will define our precision window, or let's say, which is kind of defining our epsilon. If we have a configuration that belongs to E, in particular, it means there is a 0, 0 beyond the n, and also a 0, 0 beyond the minus n. And now if C prime is a configuration that agrees with C on this whole region, D, then I claim that as you start iterating C and C prime, they will stay agreeing on this region. Well, why is that? They will, these two blocks will never be influenced by anything from the outside, and they will not allow information to go through this. And because they agree everywhere in the middle, they will agree everywhere in the middle in all the iterations. So then essentially FIC restricted to this domain D is the same as FIC prime restricted to this domain D for all iterations of I. So maybe I will go overboard for 4 more minutes and finish this. So one last definition. So suppose A is a one-dimensional CA with radius r. Okay, let's just say it's a one-dimensional CA. Let mn be 2 positive integers, m less or equal to n. So we say that U, which is a sequence of n states, is an m-blocking word for some offset p if whenever 2 configurations agree on a domain of this pattern and are exactly equal to U, then for all iterations this block with offset p all the way to m will stay the same. So a picture is like this. If there is this word U, whenever a configuration contains it, then there is some finite subchunk of U such that each 2 configurations which initially contain U at this exact same position, they will always agree on this subchunk. Yes?
Just for the definition of E, don't we need the pattern 0, 0 to be infinitely open, but on both sides to have an equicontinuity point?
Uh,
Because it could repeat infinitely, but only on the...
okay. Sure. Thank you. That's a good point. And I suppose it's the same problem here. Yeah, it's clear when we define it like this, but yeah. I should have written it more carefully. So to finish, what stands behind that proposition is this following proposition. So let A be a one-dimensional CA with radius r. Then we have two substatements. Essentially, if A contains an R blocking word, then A is almost equicontinuous. So you can imagine that it is not hard to prove this statement just based on the example we had. Essentially, if you have this word, you just again create a set which is residual of configurations that create this word infinitely often on both sides, and then you will show that this is an equicontinuity point. Yes?
I just don't understand the last definition. In the n definition, you put an equality between c from 0 to n1 minus 1 is equal to c from 0 to n minus 1. I can't see it.
C prime. So, okay, if for all C prime configurations, so whenever you take two configurations that agree on this finite region and have exactly this m-blocking word there, what does it mean? Is that in all future iterations they will agree on this subregion. So you can always keep in mind this example with the two zeros. This is a 2 blocking word, and it's of length 2, so there is no offset going on or anything. And whenever two configurations have these two zeros, they will keep agreeing on this finite region.
It doesn't necessarily have to be the same 0, 0 that stays.
Yeah, it can be different as long as it agrees for the two configurations. It could, for instance, iterate between 0, 0, 1, 1, 0, 0, 1, 1. So let's say the negation of the majority rule would also essentially have a blocking word, but it will oscillate. It's not going to stay the same. But in either case, you can use the exact same argument to show that configurations that contain such an R blocking word. So now it's important that we block R positions with this being the radius, so that really information cannot skip over this block from the outside. And the second point that is really completely straightforward to check and which holds in arbitrary dimension is that if A is not sensitive, then it contains an R blocking word. So you can just start writing the negation of the sensitivity condition. So you can pick some epsilon and you will realize that there exists some configuration which will kind of determine all the possible futures on a finite region, and this will determine the blocking word. So what is the thing that fails in higher dimensions? As I say, this statement, if you in some suitable way generalize the notion of R blocking words, would hold in arbitrary dimension, but it is this property that is very specific to the geometry of the 1D world. That is that if you already have such a block which determines all future values on some finite subblock of this, it really stops any information flow between these two infinite regions of the grid. That same block in 2 dimensions does not have the same function because information can still flow around it. So that's it. Let's start at 25.